of Oxford, and he's going to say something about advanced MD for ligand binding, successes, problems, and alternatives, but also something about neural networks. Is that right?
Yep.
Okay.
Yep, that's right. Is this on? Is this good? Okay, cool. Okay, yeah, so I'd like to start just by thanking the organizers for inviting me. It's a great pleasure. My first CCP4 weekend or week, whatever this is. So thanks for that. And yeah, I'm going to talk about some advanced MD for ligand binding, but I'm also, yeah, as Robert said, I'm just going to, in the interest of what was just said yesterday, tell you about some very recent work in the last year or so that we've been doing to do with neural nets. And I think this might be a bit more interesting for this audience, especially given the discussion yesterday. So advanced MD for ligand binding typically means tackling the problem of affinity, which was discussed a bit yesterday, the sort of holy grail, one of the holy grails at least, of comp chem, if you like. And this is often the face that you see if you tell people in my group that they're going to work on affinity. So it's quite appropriate. And usually this means under equilibrium conditions, just as a clarifier. And indeed, there are, of course, that has several caveats as well in itself. So the normal way that this is done, and this theory has been around for several decades, probably 60, 70 years, is called free energy perturbation, which you probably have all heard of. And this is the kind of standard way to compute relative binding free energies. And it's essentially relies on a computational trick called alchemistry, which results in computing basically non-physical things. So there's no physical equivalent for this. So let's say that you have, or you know, the affinity for, let's say, drug A at the top here, okay, and you want to compute or predict the affinity of compound B without actually measuring that, then you can't do this leg directly in the computer, but what you can do is these alchemical transformations on these vertical indices, vertical edges here, okay? And this alchemical transformation is usually controlled via a so-called lambda parameter, where you literally kind of morph essentially one ligand into another, okay? So that's shown here on the right. So this might be compound A, and at the bottom right might be compound B. And the only difference is basically this little methyl group that's appeared here, okay? And by integrating all of the energy difference in the system between those, in all of those different lambda values, you can essentially work out this delta delta G of solvation, or the delta delta G of the ligands in the site, essentially. And this is particularly useful for structure activity relationships. If you've just got one measurement, and you can do this, and you can do this in order to then compute or predict your affinity of in relative style of the other ligand. Now, if you don't know that, if you don't have a measured compound, then you can do the absolute binding free energy. So it's the same kind of idea. We want to kind of compute this number here. We can't do this directly, but what we can do is go around this thermodynamic cycle again. And it's a similar idea. Essentially, we annihilate in solution the ligand, or we annihilate it in the complex. And there's a few other steps here, which for technical reasons I won't bother. Well, they're for technical reasons of the actual computation, but I won't bore you with those details. The problem is that these are more difficult, way more difficult to do absolute binding free energies than relative binding free energies, because there's no cancellation of errors that you can benefit from, okay? But it does offer two distinct advantages. One is that you can tackle any combinations of ligand in your series, because in those previous relative calculations, you're usually constrained to small changes between the ligands. So that's why they're quite good for SAR series. But if you have very different ligands, it's a little bit more problematic. And you can actually do the reverse. So you can compute the selectivity of ligand for different proteins. Now, that is not routinely done hardly at all, actually, in the literature. But I'll show you an example of where we've done that in the past. So here's an example. This is quite old work that we did about 10 years ago, but it was one of the kind of first papers, I would say, that really demonstrated that absolute binding free energies could be done with a reasonable accuracy. So this is a bromodomain that you're looking at here. It has quite a nice pocket that binds acetylated lysines. And there's a whole variety of different compounds that we know bind to that pocket, and they both have crystal structure associated with them, and also ITC data to characterize the affinity in some way. And so this was one of the first things that we tackled, and it actually does pretty well. So this is actually about as good as you can get, I would say, for an absolute binding free energy. You can see here the mean errors less than a kcal per mole. So I don't think it'd be possible actually to do any better than that, actually, realistically speaking, and pretty good correlation coefficients as well. Now, you could argue, well, you started from the crystal structure there, so you cheated, right? So what about if you start from a docked position? Well, actually, yeah, you can do pretty well. It's slightly worse, but you can actually do pretty good with just starting from docked solutions as well. So this is pretty much about as good as you can get. Hello, oh, there we go. As I mentioned, you can do the reverse, which is to take one compound and then throw it against, in this case, 21 different bromodomains and try and predict the selectivity of that one compound for the different proteins that you have. And you'll see here the results are a little bit more modest. Okay, so we've got a worse mean squared error, and we've got a much worse correlation. But this is currently about where we are for this kind of problem. It's much harder to predict selectivity against different proteins because, of course, the different proteins have different flexibility associated with them, and there are much more dynamics associated to worry about with that, so your sampling becomes an issue. That's current state of the art. And what's happened in the last 10 years or so, I would say, and I'm going to summarize this up in one slide, is basically the whole field is really worried about the domain of applicability and worked on really producing benchmark data with which we can do future calculations, try and work out where the problems lie, and so on. And there are two key papers from this. One is from Greg Ross in 2023 when he was working at Schrödinger, which is a commercial company that produces software to do these kinds of calculations. And another paper came out literally last week or the week before from Hannah Baumann of the Open Free Energy Consortium. And they were benchmarking about 1,700 complexes, and the data sets comprise both public and private data sets. So pharma's really invested in this now. So 15 years ago, probably most pharma companies would not have had an MD person doing anything like these kinds of calculations. Now, quite a lot of pharma people actually have some MD person doing these kinds of calculations. And there are two things it's not my work, I just want to draw your attention to this paper because I think it summarizes a couple of key points. One is that the performance of these codes now is quite robust, right? So here you're looking at a summary of looking at one of these benchmark sets, essentially. And there's a lot of data here, but this is basically sort of kcal error on the left, if you like, and then right some measure of usually correlation. And what you're looking at is a comparison between commercial software called FEP+, and then the open free energy kind of package, if you like, which is stitched together of various free open softwares, okay? And you can see here that the performance of the free code that you can get and anybody can use is pretty comparable to the commercial software, okay? You can argue that the commercial software does slightly better, the metrics look slightly better across this data set, but in general, it's pretty comparable. There's one other interesting thing that dropped out of that paper's analysis, and that is that the private data sets, so this was the data sets that companies just sort of did in-house and then presented the aggregate data back to the consortium, that actually looks a lot harder. And that's unsurprisingly, they're obviously challenging with real-world targets that they're interested in. And you can see here the performance there across these private data sets is generally a little bit worse. And that's maybe not so surprising. So that's currently where I would say that's currently a good reflection of state of the art. So you're looking at about 1 to 1.5 kcals per mole error and a correlation coefficient somewhere around 0.5, 0.6, somewhere like that. So that's currently where we're sitting. There are many problems still with absolute or relative binding free energies. And these include things like cofactors and metals. We're not particularly good at dealing with those. Tautomers are problematic, particularly if you have something in solution that changes upon the binding event. Fragments are problematic because fragments tend to be weak binders. And so typically that means sort of 4 or 5 kcals per mole in terms of affinity. And then if your error is 2 or 3 kcals per mole, then you start to get into problems if you're trying to rank your fragments, for example. So that's still very hard to do. Nobody really is working on RNA, DNA targets. If they are, I'd love to hear from you because I don't know anybody that's really doing that problem. Membrane proteins can be difficult. They can be quite straightforward, but they can be quite difficult as well, particularly if your binding site is exposed to the interface region of the head group. It's actually not too bad if they're exposed to the lipid group, but exposed to the interface region is a bit more problematic. Water sampling can be a problem. If you've got very deep water pockets, or pockets that have waters in there, sometimes you cannot sample the water well enough in the free energy calculation to account for that, and that's also a problem. You can suffer from large perturbations upon binding as well, and that can be problematic in terms of sampling. And of course, there's always the perennial problem of worrying about the parameters, which is always a concern. But there's one thing that is a bigger challenge still, and that is the fact that most of these calculations take a few hours to complete, right? So the speed is a big problem, okay? And it takes several GPU hours currently to do one, or have confidence at least in one of these values. So what can you do about that? And that's where we started to think a few years ago now about trying to get into the sort of neural network-based type prediction approaches for this. So ML or neural network type approaches have the potential to do these things a lot faster, right? So in our hands, about 400,000 times faster, okay, which would then make it possibly an option for doing at least some kind of virtual screening. But if you look in the literature so far, they tend to struggle to rank compounds, certainly in congeneric series. They struggle to generalize, and that, of course, reflects a memorization problem. Many people here will realize that or know that. And frequently, though, they're not evaluated in a very robust fashion, which is really problematic for the field at the minute. Most of these are evaluated on a test set, which is called the CASF 2016 set, which actually has within it things that were in the training set, which is derived from PDB-bind, which is a subset of PDB itself, which has just the complexes in it. And the rather bizarre thing is that almost all of these are never evaluated against the same benchmarks that the FEP community uses. So rather bizarrely, we're all trying to do the same thing, and yet we're evaluating it on rather different benchmarks. So these are some of the things that we were trying to worry about when we were trying to do, going forward, as it were. And so I'm going to spend the next sort of few minutes just talking about some work that was done by two postdocs in the lab, Wei Si and Matt Warren, in collaboration with Isaac Valson, who's a very talented graduate student in Garrett Morris's group, and we collaborated on this particular project. So we, a few years ago, had a piece of software called AE Score, which is based on atomic environment vectors. That sounds an awful mouthful. All that really means is that we represent, in a neural network fashion, the local environment of our ligand. Okay, so we kind of derive that from our sort of ligand binding set, our training set, and we encode that into a neural network. And Isaac has then extended that into this AEV PLIGS, which basically encodes that in a kind of a graph-based network instead. So this is our own code, but there are many codes out there that do kind of similar things with neural nets, right? So just to sort of show you, the first thing you can do is obviously compare that to CASF. And that's what you can see here. And the results look pretty good, right? If you look at the Pearson correlation coefficient and the Kendall-Tau information, then you can see that actually, this is quite high. In fact, it's suspiciously good, right? And you can see here, I've just put up when we run it across lots of different models that are out there that are considered pretty much state-of-the-art, you can see these values are all pretty good at this. These codes are all pretty good, seemingly, on this test set, right? So it looks a bit bad. So we thought, well, that probably does reflect a problem with the test set. So what Isaac was working on was actually the development of a new benchmark set called the out-of-distribution test set. And the idea was quite simply to minimize the similarity between the complexes in the test set and the training set, essentially, in terms of ligand similarity, protein sequence identity, and protein pocket similarity. Okay, so you can see that summarized here, or rather you can see in the CASF set that there are some sort of examples where there are high similarity, certainly, to the stuff in the training set, right? And that's always going to be a problem if you're doing this kind of thing, right? So if we now do it against this new test set, what's the performance like? Well, it's actually not still too bad, actually, okay? So the benchmark, now you can see there's a bit of a drop, okay? The Pearson correlation and the Kendall-Tau dropped. Our error's gone up a little bit, but it's still not too bad, okay? Of course, you might think, well, what about all the other models? This is a horrendous table. I apologize for this, but I just wanted to put it up for the sake of transparency to show you that actually all of these models will show a drop in performance. Okay, so no one is winning here. We're all doing the same. There's a reassuring drop almost of performance across the board. Okay, maybe not so bad for us. And actually, this is to be expected. Work by Fergus Boyles in 2020 showed that actually a lot of information that was encoded in the ligand would actually be enough to give you a quite reasonable performance here. Okay, so there is another test set which we came across in 2023 by Durrant et al., which is called the zero ligand bias set. And this is a particularly interesting data set because its construction was designed to ensure that models that only learn ligand-based features cannot rank the binding affinity of the test complexes, okay? So it's particularly challenging to do well on this set. And as you can see, apologies for the horrendous table again, but just in the sake of transparency, now we are really all absolutely awful at this kind of task, right? So it's pretty obvious that this is a challenging data set, right? So we're still a ways off. Okay, so that's really what you should be looking for if someone's presenting you with a new neural network kind of scoring function. If they're not testing it against something like this, then you should be very suspicious of how well it's doing, actually. Now, of course, one thing that we were kind of interested in was actually the comparison back to free energy perturbation, because that's considered the gold standard, right? Everybody holds that up as this kind of hallowed thing, right? So if we do that, what did we score on the FEP benchmarks that we used? And again, it's not so great, but it's a little bit better maybe than on the zero ligand bias scale. So it's not great, but 0.41 is actually not too bad, actually, believe it or not, okay? So it's not great. So we've got a bit of work to do there, certainly. So just to pause, there's a discerning discrepancy at the minute between prediction accuracy for things like CASF 2016 and what one might refer to as more realistic benchmark assessments. Okay, and that means we need to continue to really ensure that we test on these really rigorous kind of data sets. Now, one thing that you'll notice, and I referred to, is that all of those kind of methodologies all kind of all kind of look very similar in kinds of their performance, right? And that's because they are probably all because they are derived from the same amount of training data, right? Which is this PDB bind set, okay? So is that the actual problem? Is the amount of training data the problem here? So one thing that we started to worry about or think about was whether we could augment that data set somehow, okay? So in the meantime, something called binding net appeared, which was a data set basically where people had gone into Kemble and looked for affinity measurements and then looked to see whether they could generate a complex just by template-based modeling, okay? And a similar idea came out from Mike Gilson's lab with binding DB and something called the dot congeneric series as well. And so the idea is, can you use this? Is it useful to use this kind of data? So, you know, train it on PDB bind plus binding net plus the binding DB and so on, right? And the answer is, doesn't seem to make much difference at all, right? You can see here, absolutely no improvement in performance across those three different test sets that I showed you, okay? So green is PDB bind normally, and then, I'm sure what's going on here, a bit of a disco, sorry about that. And the blue is basically if you chuck all this data all in together. And you can see there's no real change in performance at all. But rather interestingly, there is a change for the FEP benchmark, okay? So this is a slightly different presentation of the data, but essentially this red line here, this represents what you can achieve with rigorous FEP calculations, okay? So doing the most thorough thing you can do, okay? And this is our normal performance, so we're down here in the green zone. And then this is basically us trying to take a little bit of account of the similarity between training and test sets, okay? So trying to, if we reduce that down, of course, your performance goes down, as I've already shown you, okay? So the 0.9 is basically our maximum performance that we'd allowed. And then you can see, actually, if we augment this now, we actually get a really big step up in the quality or the Pearson correlation coefficients, actually. Now is as high as close to 0.6 or something like this, right? Which is really quite close now to the FEP plus benchmark, okay? So that's kind of encouraging, actually. It would suggest that for this particular benchmark, we can actually improve things by augmenting the training data somewhat. And actually, if you break it down in terms of individual families in the FEP benchmark, in some cases, our methodology will actually do about as good, or if not a little bit better, than rigorous FEP. Okay, so there's some hope here in the sense that this method may actually be useful at some point. So you obviously shown you cherry pick some nice examples there, okay? But if I'm honest about it and I show you the whole data, so Pearson on the top and Kendall Tau on the bottom, now you can see actually if you compare these individual families, they're columned by individual protein families, that's what those are, then generally speaking, FEP still does much better, but the ML performance is actually not too bad, okay? So I think there's it's looking pretty promising in this case. Now, moreover, the amount of extra data that we add seems to improve things, right? So if you look at this graph, which shows you the correlation between the mean Pearson correlation coefficient and the percentage of additional augmented data that we're adding, then you can see this is still looking like it's going up, right? Which suggests that actually, if we're able to augment that even more, we might still get some improvements, okay? But how to get more data, right? Because we're sort of at a brick wall almost, right? Now, two things happened in the last year or two. One is that PDB-bind started to charge people to access the recent releases. So we actually had to switch to something called the HiQ-bind dataset as the experimental reference. You can think of it like PDB-bind, but now for free, okay? And Binding Net 1, the people who designed that also released another version called version 2, where they had claimed to expand out the number of complexes via template-based modeling again. So what happens now? Well, you can see here, this is HiQ-bind. This is like PDB-bind, so similar kind of result here than compared to what I showed you with PDB-bind. So that's all good, right? All reassuring. And then you can see there's a similar increase in the Pearson, in the correlation metrics going up. So that looks good. But what is perhaps surprising on first glance is that if you add basically a 7-fold increase in the amount of data, there's absolutely no increase in the performance again, right? Oh, so what's going on in this case, right? Has the augmentation amount effect plateaued, or is there some other problem here, right? And it turns out that if you look at the quality of the complexes in version 2, they are pretty poor, okay? So this is a kind of way of assessing that by looking at the so-called Schaaf's hybrid score. And you can see Binding Net V1, if it's about 1.5, that's generally not too bad, okay? It's considered a word on the street sort of number that's a reasonable structure. You can see here that Binding Net V2 has a large shoulder on the left, okay? And so all of those structures are really not very good for training. That's what it tells us, okay? And so that's unsurprising, right? I mean, the quality of structures matters. We've heard a little bit of discussion about that already today, right? So this is kind of reassuring that the quality of structures matters as well, okay? And just in case you thought, oh, it must be your crappy neural network model and maybe it's all fine for everybody else's, well, we ran it against a couple of other ones of these. This is, for example, the EHIG-N, which is another graph-based neural net predictor. And you can see pretty much the same trend is maintained and pretty similar results as well, actually. And the same is true for RF score as well. Okay, so the other thing that has happened, of course, in recent years, and you all know about this, is that co-folding models have come along, right? So perhaps we could use these to augment the data instead, right? Okay, but we've already said that the synthetic data matters in terms of its quality, right? So the first thing you have to do is be able to think about how we can identify reliable predictions in the absence of any reference structure, okay? So in order to try and do that, the first question we had was to establish how well does bolts 1 or 2 reproduce this HiQ-bind data set, okay? So that's what you're looking at here in this kind of Shanky type diagram. So HiQ-bind has about 30,000 structures, okay? You can divide them into single or multi-chain. Then we first basically then assess whether they pass the PoseBusters test. So PoseBusters is a program that assesses the physical quality of these predictions and basically ensures that they are chemically sensible, essentially. Then we put it through Boltz's own measure of confidence, right? Because ultimately we're going to have to see if that's good enough as a reliable metric for us to trust those structures to augment our data, okay? And then we finally measure, we have a metric of the quality of that structure, because in this case, we actually know the answer. And in that case, we actually compare that to I should actually say pocket RMSD, okay? So we can argue about which kind of metric you want to take as the measure of quality, but yeah, quick and dirty thing is just to say, what's the pocket RMSD in this case? So if it's less than 2, we say, oh, that's a high quality structure, okay? So what you can see is that actually, you know, that it does a reasonable job of maintaining a high proportion of the high confidence structures here. So you can see here, we go from 13,000 structures to about 11,000 structures, okay? So that's quite useful, I think, still, okay? So that's the important thing that steps out of this analysis. But, of course, Boltz contains most of HiQ-bind in its training set, right? So it's probably still memorizing, right? So that's a problem. So how do we get around that problem? Well, we can assess the performance of Boltz on a different data set that also came out earlier, or late last year, or middle of last year, called runs and poses data set. Okay, and this was a data set that was constructed deliberately after the construction of AF3 and bolts as well. Okay, to specifically test memorization issues. Okay, so now we can not worry about the memorization effect, or at least worry about it a little bit less. And now we can see how well bolts does in predicting these structures. Okay, so again, so now we can see that, again, same kind of idea. We've got far fewer structures in this data set, and it starts off at 2600, but you have to filter out some of the structures because for various different reasons. But essentially, you get down to the same kind of idea that by the time you get to the high confidence zone, then most of those structures are considered to be high quality. Okay, which is good, right? It's reassuring going forward. Okay. So if you then use a bolt structure, bolts generated structure, or an experimental structure in our FEP benchmark, does it matter? And the answer is no, actually. Okay, so the performance of our AEV PLIG system on the FEP benchmark is basically the same, depending on it doesn't really matter whether you use the bolts-derived structures or the experimental structures. Okay, so that's kind of encouraging, right? It means that there might be some scope for augmentation going forward, right? And I think that's quite useful to know. Finally, I just want to sort of address something that also was made, a claim that was also made in the Bolts 2 preprint, which said that they were getting close to the FEP benchmark. And in our hands, we can't do that. We can't get close to the FEP benchmark using Bolts 2. It's about as good as what we can do. Okay, so this is on the left is the Pearson coefficients, on the right is the Kendall-Towles again. Here's our AV PLIGs model, okay? And then this is various different ways of running bolts, okay? And you can see no matter what we do, we cannot get close to the FEP that's the benchmark computed by rigorous FEP methodology called FEP+. We cannot get close to that. It's always as close as any other neural network kind of model, okay? So I don't think that claim will stand scrutiny going forward. So in summary, I talked a little bit about rigorous ABFE or RBFE as being the most accurate method out there. That is still true, okay? The ML methods are faster, a lot faster, right? And they're catching up. So I think there's hope that we will be able to do this a lot faster going forward. And data augmentation has promise, but it will depend strongly on the quality of the data. That is not a surprise, I hope, right? And you'll hear, I think, a little bit tomorrow from Fergus, who's on the Open-Bind project, who's trying to solve that problem from a different way, which is to solve lots and lots of structures instead, okay, to augment that data set in a different way. And bolts is useful, but the recent claims are on affinity are overhyped for sure, okay? And I just thank everybody in the group, and particularly Wei Si, who led a lot of this kind of neural network analysis that I just spoke about in the last 10 minutes or so. And with that, I thank you for your attention, and I'm happy to take any questions.
Questions for Phil?
Hi there, Phil. Sophie Korea from Evotech. Thank you so much for your presentation. I had a bit of a question regarding your augmentation. So if you have a flexible system in which the binding pocket is mobile and you don't have that many structures, if you're doing this augmentation based on prediction, wouldn't you bias more the data, given that you do have this cutoff of the RMSD on your binding pocket?
Yeah, that's true for sure. Yeah, you're going to have a bias towards that. We could take care of that in some way going forward. We've done quite a lot of work of using reduced MSA subsampling to generate alternative conformations. So we do have quite a lot of experience of using that as a way of generating alternative conformations of the same thing. So we could get around that a little bit, maybe with that kind of approach. Thanks.
About this. Open the mic, please.
I have a question about this issue of data quality. So there are many kinds of data in this process, many measures of quality.
Yeah.
How much attention has been paid, or how much analysis has been done on the effect of just raw structure quality at the crystallographic level? Are you happy with 2.5 angstrom resolution?
Yeah.
And if you have in the same family other structures going down to 1.2 or 0.8, What difference does it make? Is it possible to detect that difference?
Yeah.
And how much attention is focused on this?
It's a very good question, and the answer is not much, is the honest answer about that. And the reason for that is not an unwillingness to do it. It's just that by the time we do some of this, we end up with quite even smaller amounts of data at the minute. And we know that that's a problem. So it's not because we don't want to do it necessarily, but someone should definitely do that. But I think we'll find that it's probably going to be more influenced by the amount of data that we have in the training. So.
Either a very, very quick one, or we go for coffee.
Oh, yeah.
One from Slack. Okay.
How did you filter the high confidence bolts-shoe prediction when you try to generate data for augmentation?
Yeah, so that's done according to Boltz's own high confidence metrics. There are quite a lot of those actually that you can pick from. I can't remember exactly what we did. It is in the paper. If you want to read the SI, that's all detailed in the paper. But yeah, but it's basically nothing different from what Boltz would have done in claiming their own high confidence metrics.
Okay, coffee time. Let's thank all the speakers and